Welcome to our next chapter. We will be studying waves again and the property of refraction, and then we will apply that idea to lenses. So remember that refraction is when a wave comes in at one medium and then it hits a boundary for a second material, and instead of passing straight through or reflecting, it's going to bend as it goes from one material to the other. You could also have the light bending outward this way. It's an either or. It's going to bend inward toward this normal line or outward towards the surface between the two materials. So you'll see both applications. Now, in order to tell which way the light or our waves will bend, we are going to look at a property called the index of refraction, and its variable is a lowercase n. You can think n for index. Sometimes you might also see this property called optical density, so just be aware you can go by either name. For our formula for index of refraction, we're going to use a lowercase c divided by a lowercase v. The lowercase c is the speed of light in a vacuum, and this number is a constant. It will always be 3 times 10 to the 8th meters per second. That's a number you might want to memorize. So to find a material's index of refraction, we'll take the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second, and we'll divide it by the speed of the light in the medium or that particular material. Notice that the units will cancel out because we're going to have meters per second divided by meters per second, and those will cancel. So we're going to see an n value that's just a number. And then the index of refraction values for various substances or materials will be provided for you. Now, using this idea of index of refraction or optical density, we can determine the angle at which a wave, particularly a light wave, will be bending as it goes from one material to another. And in order to do that, we're going to use what's called Snell's law. And the Snell's law is going to have an incident side that's denoted with I's and a refracted side, which is denoted with R's. And then I also made you a note right here. Typically in our word problems, we'll have light traveling from one material into another. The from part would be our incident material, and the into part of the problem will refer to the refracted part. So we're going to have index of refraction times the sine of the angle equals index of refraction times the sine of the angle for our two different materials. And remember, both of these angles should be measured from the normal line, not from the surface. So if you want to take a moment and make a note of that, that would be a good idea. So most of what we have left for our notes today will be example problems. So I'm going to do some with you and then also let you try some on your own as well. So we're going to start out with light traveling through an unknown transparent substance at a speed of 2.15 times 10 to the 8th meters per second, and we're interested in the index of refraction for that particular material. So when we see index of refraction, we're going to need to know the n value. So my formula looks like this. I'm going to say c over v. The c is the speed of light in a vacuum, which is always 3 times 10 to the 8th meters per second. And then we were given the speed of light in that particular material, and it was 2.15 times 10 to the 8th meters per second. Again, notice that our units cancel, and when you type that into your calculator, you should get a value of about 1.4. A friendly reminder to be careful of dividing by a number in scientific notation. If you use the EE key for easy exponent, you do not have to worry about parentheses, but if you're one of those people that says times 10 caret 8, you do need to type parentheses in the denominator when you put that in your calculator. So next, you are told for number 2 that diamond has an index of refraction of 2.42. So we're going to write that number down. And it wants to know how fast light can travel through the diamond, which will be a v. And remember that the speed of light is always 3 times 10 to the 8th meters per second. So our formula looks like this, and you simply need to rearrange. If you have a problem like this where you've got a fraction on one side and not the other, and you're kind of rusty on how to rearrange that, or that gives you trouble, pretend that the first side is divided by 1, and then you can cross multiply So n times v equals c times 1, which is just a c. And now that I have everything in one line, it should be easier to see that you would divide by the n on both sides. So when you go to plug your numbers in to calculate the speed of light in diamond, you will be dividing c over n. So try that out and check your answer. And you do see that you get a fairly large number, so I would recommend writing it in scientific notation. So that would be about 1.24 times 10 to the 8th. And then we had meters per second divided by no units at all, which would leave us with meters per second. Next, we're going to apply Snell's law. So we have a light beam in air making an angle of 40 degrees with the normal to a glass window pane, which has an index of refraction of 1.44. And we're looking for the angle at which the light gets refracted. And sometimes it's helpful to draw a picture, so I'm going to go ahead and do that for you. So I have air up on the top, and then my glass window pane is the material underneath, and this represents my normal line. So when my light ray is incident at 40 degrees with the normal, I would know that right here would be 40 degrees, and I want to know the angle at which light comes out. I don't know if it's going to bend outward or inward, so we're going to do the math and figure out how the light is going to look once it refracts through the glass. So I'm going to start out with Snell's law. So anytime you see a math problem that's got index of refraction and angles in it, this is going to be your formula. And we know that light is traveling from air into the glass. So the from will be our incident side, and into the glass will be our refracted side. Now air has an index of refraction value that's barely over 1. I believe it's 1.0003. Typically, we just say that it has an n value of 1. So if you ever see air, that's an easy one to remember. And then the sine of the angle would be 40 degrees because it was already referenced to the normal line. Had it said at 40 degrees to the glass, we would have had an angle down here, and you would have had to subtract from 90 to get the actual incident angle. So don't forget to look for that reference to make sure that your angle is measured from the normal line. And then for the other part of our formula, we know that it's going into the glass. So the glass index of refraction value is given to you. And then we are simply looking for the refracted angle. So in my calculator, and I made you a note that you definitely want to be in degree mode, I'm going to say the sine of 40 times 1, which will just be the sine of 40. And then I want to divide both sides by the index of refraction for my glass, which is 1.44. And this will leave me with the sine of the angle. So take a moment and put that in your calculator. As long as you're in degree mode, you should have gotten the sine of the refracted angle is equal to about 0.4464. Now on this part, you don't want to round too early, so it's a good idea to leave at least 4 decimal places, or we can use the answer that is stored in your calculator. But we do have one more step. See how it's the refracted angle? We want to get rid of that sine, and the way that we do that is to take the inverse sine of that number. And I'll show you how to type that on your calculator as well. So on your calculator, you want to hit the second button and then sine, and this will give us the inverse sine, and then follow that with hitting second and then the negative sign key, which is down by the enter button. And what this does is it types in the stored answer from the previous problem that we did right here. And then you can hit enter, and you should get a refracted angle of 26.5 degrees. Now what this means for our picture, this 26.5 degrees would be measured from the normal line. So when this light comes in and refracts, I'm only going to have an angle right here of 26.5 degrees. So that tells us that the light is going to bend more toward the normal. And just looking ahead a little bit, whichever index of refraction value is higher, so 1.44 was higher than 1, that side or that material is going to get the smaller angle. So for this one, I'm going to get you set up with the problem, and then I would like for you to try it on your own and come back and check your answer. So we have a ray of light traveling from air into water at an angle with the surface of 60 degrees. So if we think about our surface and then our normal line, the light is going to travel from air into water. So the air is up here and our water is going to be down here. And notice that it said at an angle with the surface of 60 degrees. So this is 60, but we need an angle of incidence that's measured from the normal line. So right here is going to be our theta I, so don't forget to subtract from 90 to get that actual incident angle. So you should have these quantities listed. It's going from air, which will be our incident side. Air is an index of refraction of 1, into water, which is the refracted side, and you're given the index of refraction of water is 1.33. And then remember, we found our angle of incidence as 30 degrees. So part A, you're looking for the angle of refraction. That's going to require you to use Snell's law. So set up the problem and work it out just like we did before and see if you can get the correct angle of refraction value. So I walked you through the steps in case you missed it. I showed you all the work, and you should get about 22.1 as your answer. Now part B wants to know the speed of light in water. So we do have two n values, but you want to go by the one for water when you go to find the speed of light for that substance. So for part B, we're going to use the formula N equals C over V. Go ahead and rearrange that for V and do the math, and then come back and check your answer. You should have gotten 2.26 times 10 to the 8th meters per second. And lastly, we just have some additional notes to summarize the behavior of light rays as they travel from one medium to another. So the angle in the dense medium is always smaller than the angle in the less dense medium. So you can remember, the denser the medium, the smaller the angle. And then if you are going into a more dense medium, so from a small n to a large n, that means that light will bend toward the normal, and our picture will look like this. And then if light is going into a less dense medium, from a larger n to a smaller n, then light will bend away from the normal. And that picture would look like this. So we're going to have a lab where you're actually going to do the sight lines like we did for the flat mirrors, but you're going to be looking through a material, and we're going to see how the light or the line of sight will get refracted in different materials. That's it for today. Our next lesson, we will apply refraction to lenses.